What if a comet from another star entered our solar system? And the most disturbing thing about it was not its speed, but its age. What if, for a few short months, sunlight opened a frozen archive that began its story before our sun was even born? And before we go further, do me one quick favor. Tap, like, if you enjoy mysteries that actually make you think. Subscribe if you want more stories like this, and share this with the friend who always says space is just empty rock. On July 1st, 2025, a telescope in Chile spotted a faint moving blur. At first, it looked like one more tiny object in a crowded sky. But the math changed everything. Its orbit was too open, its speed was too high. It was not circling the sun like a normal object from our own cosmic neighborhood. It was passing through. It came from outside the solar system, and once it left, it would never return. The object was named 3I Atlas. The label sounds dry, but it carries a shocking meaning. The 3I means third confirmed interstellar object ever seen by humanity. Only the third. In all the years we have spent watching the sky, building observatories, and dreaming about what moves between the stars, we have confirmed just 3 visitors from somewhere else. That matters because the galaxy should be full of debris. Young planetary systems are violent places. Giant planets move. Ice and rock get thrown outward. Broken leftovers are launched into deep space and spend billions of years wandering alone. Scientists have long suspected that interstellar objects must drift through our solar system more often than most people realize. The problem is not that they never come. The problem is that they are small, dim, fast, and easy to miss. We only started catching them recently. In 2017, astronomers found Oumuamua, the first confirmed interstellar visitor, and it triggered endless debate because it did not behave the way many expected. Then, in 2019, came 2I Borisov, which looked much more like a familiar comet. 3I Atlas felt different again, not because it looked artificial, not because it flashed some message, but because almost everything about it pointed toward deep age. After the discovery announcement, astronomers searched old images and found that 3I Atlas had already appeared in earlier observations from mid-June. That happens often in astronomy. First you notice the intruder, then you realize it had already been crossing your vision in silence. But once its path was reconstructed, one conclusion was immediate. This thing was on a hyperbolic orbit. In plain English, it was moving too fast to be trapped by the sun. Gravity could bend its path, but it could not keep it. And it was moving with purpose. Something in another star system had thrown this object out long ago, probably through a violent gravitational encounter. A giant planet, a shifting early system, a close brush with something massive. We may never know the exact event. We only see the result. A frozen traveler flung into the galaxy, crossing the dark for an almost unimaginable span of time. That is the part worth slowing down for. Before Earth had life, before Earth had oceans, before the sun even existed, 3I Atlas may already have been freezing in darkness somewhere far away. Then it was kicked loose and began a journey so long that human history vanishes beside it. Every kingdom, every invention, every war, every piece of music, every memory ever held by our species could fit inside a sliver of the time this object may have existed. That is why scientists moved so fast. They were not just watching a comet. They were staring at a sample from a place, an era no spacecraft has ever visited. Very quickly, major telescopes on Earth and in space turned toward it. Hubble observed it. Webb observed it. Large ground observatories tracked it. Researchers around the world tried to squeeze every possible clue from a visitor that would only give them one chance. Because 3I Atlas was not like a rock stored in a museum drawer. It was a passing archive. Miss the moment and the archive closes forever. Hubble helped show what happened as sunlight warmed the object. A cloud of dust and gas wrapped around the nucleus. That was important right away. Unlike Oumuamua, which confused people because it did not show the normal visual behavior of a comet, 3I Atlas clearly behaved like an active comet. It was releasing material. It was waking up. And that gave scientists something precious: chemistry. Comets matter because they store ancient ingredients. Their ice and dust can trap molecules for extraordinary lengths of time. When sunlight heats them, gas escapes. That gas can be studied. Light breaks into patterns. Patterns reveal molecules. Molecules reveal conditions. And conditions reveal history. So the biggest question was not simply, what is this thing? The bigger question was, what kind of past is trapped inside it? Even the size of the solid nucleus was hard to measure at first, because the bright cloud around it made direct observation difficult. Early estimates were wide. Later work narrowed the picture. The nucleus appeared to be a few kilometers across, large enough to matter, small enough to remain far beyond physical human reach, a distant body from another system, hidden inside its own glowing breath. Then the chemistry results arrived, and this is where the story stopped being merely exciting and became quietly unnerving. Not because scientists found alien machinery, they did not. Searches for artificial radio signals found nothing persuasive, and mainstream scientific judgment stayed on the side of a natural comet. NASA and other researchers treated 3I Atlas as what the evidence strongly supported. A real interstellar comet, but an extremely unusual one. That distinction matters. Natural does not mean ordinary. Webb and other observatories found that the chemistry of 3I Atlas did not match what scientists usually see in comets from our own solar system. The object appeared unusually rich in carbon dioxide compared with water. Later, Webb directly detected methane gas. That was the first direct methane detection on an interstellar visitor. The methane results stood out not because it proved life, but because methane is volatile. It evaporates easily. If it shows up this way, especially after the comet's close pass by the sun, it suggests some of that material was buried deeper below the surface and only emerged after heat reached the subsurface layers. But methane was only part of the story. The more powerful clues came from isotopes. Scientists found unusually high levels of deuterium, also called heavy hydrogen, along with unusual carbon and nitrogen isotope ratios. Those details may sound technical, but they are like fingerprints from the object's birthplace. They tell scientists about temperature, chemistry, and the broader environment in which the material formed. And the fingerprint did not look like home. The deuterium result pointed to formation in an extremely cold environment, around or below 30 Kelvin. That is brutally cold, the kind of cold where ancient chemistry can be preserved for vast spans of time. The carbon data pointed toward an old, low metallicity environment, meaning a star system formed when the Milky Way itself was younger and contained fewer heavy elements than it does today. In simple terms, 3I Atlas did not appear to form in a young, familiar setting like our own. It may have formed more than twice as long ago as the Sun. That is the number that changes the emotional temperature of the story. Our solar system is about 4.6 billion years old. Evidence from multiple studies suggested that 3I Atlas could be roughly 11 to 12 billion years old. Not a little older, vastly older, old enough to have formed in an early chapter of the Milky Way, when the galaxy was chemically different from the one we inhabit now. Quick pause. If this story is already pulling you in, leave a comment emoji below. Subscribe so you do not miss the next deep dive, and send this video to one person who still thinks the biggest mysteries are all behind us. Now think about what that means. This was not just an object from another star system. It may have been a preserved fragment from the early Milky Way, a body that locked away ancient conditions long before Earth existed, long before the sun burned, long before anything human could have imagined such a thing. And it came close enough for us to study. Not to land, not to slow down, not to explain itself in words, just to pass through our light, warm slightly, and release clues. That is why scientists cared so much. The real value was comparison. If 3I Atlas truly formed under such different conditions, then our solar system may not be the standard template we once assumed. Maybe the mixture of ice, gas, and organics that shaped our comets is just one version of a much larger galactic pattern. Maybe other systems formed under colder, older, harsher conditions. Maybe the early galaxy produced icy bodies with chemical inventories unlike anything we have sampled up close before. And that leads to an even deeper question. Could some of those ingredients matter not just for comet science, but for the story of life? When researchers discussed 3I Atlas, one phrase kept surfacing in the background: prebiotic chemistry. That means the chemistry that can come before biology, not proof of life, not hidden microbes, not a dramatic alien reveal. Just the raw molecular groundwork that, in the right environment, can contribute to more complex chemistry. That matters because one of the biggest questions in science is whether the steps leading toward life happen easily across the universe, or only under rare conditions. If molecules important to that process can form in many places, and if icy bodies can carry them across enormous distances, then the raw materials of living chemistry may travel far more widely than we once thought. 3I Atlas did not settle that question, but it made it harder to ignore. Scientists detected water, carbon dioxide, methane, and other compounds tied to carbon-rich comet chemistry. The exact mix was unusual enough to force new questions. How different can interstellar comets be from our own? How much early galactic chemistry can an object preserve? Are some of the building blocks associated with life common across very different stellar environments? This is the point where public imagination often rushes straight toward aliens. But science does not move well through giant leaps. Methane can be produced without life. Strange chemistry can come from extreme cold, deep burial under ice, radiation, or processes we still do not fully understand. The evidence did not show alien technology. It did not prove extraterrestrial organisms. But it did show something genuinely profound. The universe has been running chemical experiments for far longer than Earth has existed. That alone is extraordinary. Imagine an object forming around an ancient star, carrying frozen material from a brutal, distant cold, then being thrown into interstellar space and preserved for billions of years. Imagine it wandering the galaxy, untouched by nearby sunlight for ages. until chance brings it into our system and our telescopes catch it just as our own star begins to unlock its deeper layers. That is not fantasy. That is almost exactly what happened. There's also a hard truth buried inside this story. We were not ready. Our observations were impressive, but we were still spectators. No spacecraft rushed out to meet 3I Atlas. No probe hovered beside it. No mission drilled into its surface or tasted its dust directly. Not because scientists lacked interest, but because interstellar visitors do not announce themselves far enough in advance. They arrive fast. They are discovered late. They leave quickly. If the systems, missions, and plans are not already prepared, the opportunity vanishes. That may be one of the biggest lessons of 3I Atlas. The next interstellar object will come. Maybe not soon. Maybe sooner than anyone expects. But when it does, we will want more than telescope data. We will want a fast, serious attempt to intercept it, because each of these visitors is more than an object. It is evidence from somewhere else, and rare evidence carries a special weight. There is an emotional side to that weight. Human life feels long from the inside. Civilizations feel old to the people living in them. But beside something like 3I Atlas, we are almost flickers. This comet may have existed through most of the galaxy's life. It is older than our species by such a ridiculous margin that language almost fails. It crossed all that time, entered our solar system, and for a brief moment let us inspect what it was shedding into space. That does something to the mind. It forces you to feel history at a scale that the human brain was never built to hold comfortably. And then there is the central tension in this entire story. It is not really whether 3I Atlas was artificial. That is the flashy question, but it is the smaller one. The deeper question is whether chemistry, this old and this strange, travels through the galaxy more often than we realized. How many worlds have been brushed by frozen couriers carrying complex carbon chemistry? How many young systems received material formed around older stars? How often has the Milky Way mixed and scattered ingredients across enormous distances? 3I Atlas did not answer those questions. It sharpened them. And that may be even more valuable. The best discoveries do not just solve mysteries, they create better mysteries. Before this, we could only speculate in general terms about the chemistry inside an ancient interstellar comet. After 3I Atlas, we have real isotope measurements, real molecule detections, and real evidence that at least some interstellar visitors carry chemical signatures unlike those of our local comets. That is not the end of the story. It is the beginning of a stronger one. There was something almost poetic about the way the object unfolded. At great distance, it was just a faint target. As it neared the sun, it brightened and released more gas. Later, scientists saw evidence that deeper material, including methane, had begun escaping from below the surface. Sunlight was, in a sense, opening the archive layer by layer. Our telescopes read a few pages before the book closed again. By early 2026, 3I Atlas was already moving away, fading, slipping back toward the dark beyond the planets. Soon it would be too far for this kind of detailed study. No second pass, no return visit, just one more silent crossing through the Milky Way. That should make us a little uneasy. Not because it was dangerous in some movie-style way, but because it reminded us how limited we still are. A thing this old, this rare, and this informative passed through our neighborhood, and the best we could do was watch from a distance. That is not failure. It is a reality check. We are still early in the long story of learning how to study the universe. And that brings us back to the idea of a strange signal. Did 3I Atlas send one back? Yes, but not a radio message, not a coded beam. Its signal was chemical. Its signal was isotopic. Its signal was the mismatch between what it carried and what our own solar system usually produces. Its signal was age. Its signal was the fact that multiple teams had to pause, compare, test, and ask whether they were looking at a normal comet formed in very unusual conditions or a larger clue about how the galaxy builds icy worlds. That is what real scientific investigation looks like. Slower than internet hype. Stronger than internet hype. One team measures deuterium, another studies carbon, another checks nitrogen. Another models the kind of birthplace that could produce such values. Another examines how the gases changed as sunlight warmed the object. Piece by piece, a picture emerges, and the picture was remarkable. 3I Atlas most likely formed in a very cold environment around an old star system with low metallicity, then preserved that early chemistry for billions of years before wandering into our neighborhood. That is a calm sentence hiding an enormous fact. It means human beings were able to study a sample of galactic history, older than the solar system itself. And that makes this more than a comet story. Everything you are depends on chemistry, every cell, every breath, every thought. So when a body from another era enters our system carrying a chemical history very different from our own, this is not just a story about rock and ice. It is a story about origins, about how many roots the universe may have for building complexity, about whether the raw ingredients connected to life's beginning are local accidents or widespread possibilities. If you have stayed with me this far, you are exactly who this channel is for. So here is your quiet invitation. Like the video, subscribe for the next investigation, and share this with one person who loves big questions more than easy answers. Now go one layer deeper with me. There is a comforting human habit of treating our solar system as the standard for everything. We compare other planets to Earth, other atmospheres to ours, other comets to our own. That is understandable. Home is the only full example we have, but it can also fool us. What if our local chemistry is just one dialect in a galaxy full of different chemical languages? What if 3I Atlas is not the odd exception? What if future discoveries show that many interstellar comets formed in older, colder, stranger environments than the one that shaped our system? That would reshape far more than a few comet papers. It would affect how we think about planet formation, chemical transport, and the distribution of life-friendly ingredients across the galaxy. There is also the question of survival. Interstellar space is harsh. Radiation, impacts, and slow physical change should rewrite some of these objects over time. Yet 3I Atlas seems to have kept enough of its original story that scientists could still read meaningful parts of it. That suggests interstellar objects may be better archives than many once hoped. Not perfect archives, but real ones. And that opens a new frontier. Interstellar objects are not just rare visitors, they may become tools of galactic archaeology. Instead of studying the Milky Way only through distant light and computer models, we may sometimes study pieces of its past as active bodies that drift directly into our system. There is one more thing that gives this story its strange power: chance. So much depended on luck. The object had to pass close enough to be detected. Our surveys had to be running. The sky position had to work in our favor. The brightness had to be high enough. Scientists had to react quickly. If only a few details had changed, 3I Atlas might have crossed the inner solar system completely unnoticed. How many have already done exactly that? That question matters because interstellar objects may be more common than older estimates suggested. We only recently built sky surveys good enough to notice them. If so, then the third confirmed interstellar object may be remembered, not just for its chemistry, but because it arrived at the moment human observation was finally becoming sharp enough to learn something serious from such encounters. That is why the story feels almost personal. It catches humanity mid-transition. Smart enough to notice, not yet fast enough to touch. Curious enough to ask the right questions, not yet prepared enough to chase the answers physically. We are in that beautiful, awkward stage where the universe is revealing deeper layers, and our tools are just barely keeping up. That is also why the unanswered questions matter so much. Is methane like this common in interstellar comets? Are the extreme isotope ratios rare or typical? How much prebiotic material do these objects usually carry? Could a fast response mission one day fly through the coma of the next visitor and sample its dust directly? Right now, we do not know. But now we know what we want to know. And that changes everything. 3I Atlas turned vague wonder into a plan. Improve the surveys, speed up follow-up observations, prepare mission concepts in advance, design instruments for rapid chemical analysis, treat the next interstellar visitor not as a passing headline, but as a scientific opportunity too important to waste. That plan is not abstract. The next generation of sky surveys will search faster, deeper, and more often than anything that existed for most of human history. That means the next interstellar visitor might be found earlier, while it is still far away, before sunlight changes too much and before the clock becomes impossible. An earlier discovery changes everything. It gives scientists more time to coordinate telescopes, refine the orbit, compare models, and maybe, if we are bold enough, send something out to meet it. Think about how different this story would feel if we had images from a few hundred miles away instead of a few hundred million. Think about seeing the jets directly. Think about mapping the surface, tracing the layers, sampling the dust grain by grain, and measuring the chemistry without guessing through a glowing cloud. The leap from watching to touching would not be a minor upgrade. It would feel like a new age of discovery. And maybe that is why 3I Atlas feels less like a finished chapter and more like a warning bell. Not a warning of danger, a warning against passivity. The galaxy is sending us material from places we cannot visit yet. If we ignore that opportunity, we ignore one of the cleanest ways to study worlds beyond our own. But if we prepare, the fourth or fifth visitor might answer questions this third one could only raise, because even without a spacecraft, 3I Atlas already left a mark. It reminded us that the galaxy is not divided into sealed islands. Material travels between stars. Ice travels, carbon travels, ancient chemistry travels. Things formed elsewhere can enter our system carrying memories of environments we never saw. The line between our story and the galaxy's story is thinner than most of us ever felt. So when people ask why scientists cared so much about a faint comet from another star, the answer is simple. Because it was not just a comet, it was a preserved fragment from an older cosmic chapter, a piece of chemistry written before our sun turned on, a traveler that crossed billions of years and briefly let us inspect the materials of another age. And in doing that, it made one fact feel impossible to ignore. The universe has been setting up possibilities for much longer than we have been around to notice them. That truth is humbling because it reminds us how late we are to the story. And it is thrilling because it means the story is vastly bigger than our small beginning. 3I Atlas is gone now, retreating into the dark beyond the planets. It will keep moving long after every person watching this video is gone, long after our cities change shape, long after our current arguments feel small and ancient. It will continue carrying its hidden layers through the cold, perhaps toward another star, perhaps past empty space, perhaps through silence for ages beyond imagination. But for one brief moment it passed through our light, and in that light it told us something beautiful and unsettling at the same time. The universe may be older, stranger, and more chemically creative than we ever truly felt in our bones, which means the next time a faint blur appears on a telescope screen, scientists will not just see another object. They will see a possible archive, a possible messenger, a possible clue. To how often the raw ingredients of life are mixed and scattered across the galaxy. A possible answer, wrapped in 100 even bigger questions. So maybe the strangest signal 3I Atlas sent back was not methane, or deuterium, or exotic carbon ratios. Maybe the strangest signal was this. We are finally advanced enough to hear the universe whisper, but not yet advanced enough to catch it before it moves on. And if that does not leave you with wonder, I do not know what will.